All right, so today we are going to be working on 3.7.
Hi, Bob.
Yeah, I have a question in the homework. Can we go over it or not? I wouldn't like to.
I'm thinking that we'd finish early, so I probably can take questions after. But I want to get through this. This is the last thing we're going to need for the test,
Which is on Monday.
which is on Wednesday.
Wednesday.
So you want it on Monday, right?
I'm just making sure.
You want to be on Monday, all right?
Due diligence.
You have to make sure we suggest.
I was like, damn, it's on Monday. I thought it was Wednesday. I was like, okay, you are the time that I have.
Yeah, so I was thinking on Monday, if we have any questions, we can just like have maybe a mini review session or something.
Wait, is it Wednesday, April Fool's Day?
Yeah.
Yeah.
Poetic. I did that on purpose. I was gonna make it Monday, and then I was like, oh, it's April Fool's.
Just sort of F with you guys.
Okay. So technically 3.8 is also one of the topics we're doing, but on the test, I'm not going to really hold you responsible for that. This is the one that usually shows up on a final, so I think testing up to here is good. 3.8 is just the non-homogeneous case of what we'll be doing here. So that one will be just when we get to it. We're going to study one application in particular, the motion of mass and vibrating spring.
Too late.
Yeah. What? Oh wait, wouldn't you do this in 207?
207, but then also it's in waves.
It's sort of mechanics. It's a spring, so it's a mechanical system. Some preliminaries before I actually give you the setup. There are some things you should be aware of. Preliminary one, which I call P1. If u of t is our position function, which is the notation we'll be using, then u prime of t would be
Velocity.
the velocity function. Let's see if you guys remember your Calc 1. And u double prime, acceleration function. Okay, just in case you forgot, now you remember. Preliminary 2. There's the second thing I wanted to talk to you about. Newton's second law of motion. Anyone knows what it is?
Force equal to mass times acceleration.
Force is equal to mass times acceleration. We're going to be using that idea. In fact, I'm going to use it now. We can write if we're talking about a certain object with mass m, then the force at any given time is given by the mass times the acceleration at any given time. We're going to be using this. Did I name this equation? Yes, I did. Call this equation 1. It's something that we're going to come back to, and it applies because of Newton's second law of motion. P3, Newton's third law of motion.
Oh my God.
Who knows that one?
Mathematically?
It's
a statement.
It's the statement. Yes, that's correct. What is it?
Totally.
Every
Anyone.
action has an equal and opposite time reaction.
Right. To every action, there is an equal and opposite reaction. Who knows Newton's first law of motion?
An object that is in motion is likely to remain in motion.
Right. Unless acted upon by an external force, blah blah blah. You're right. That's the law of inertia.
I
Right.
think you
For
were
every
action.
action, there is an equal and reaction. Preliminary, did I say anything else about that? No, preliminary 4. It's sort of going back to preliminary 2, but I just want to make it specific what kind of forces we're talking about. If I ask you about weight, right, W is weight, which you might remember is a force. That would be equal to mass times gravity, right? Which is the acceleration due to gravity.
We'll be working in feet or meters?
Either. I'm going to give you the units that you need. Again, this is mass. And this is just a specific application of that. We will take G equals 32 feet per second squared,
Okay, we're working.
or G equals 9.81 feet per second squared, meters per second squared. Depending on the context, right? You sort of have to make sure your units are consistent with everything that's going on. One thing I want you to note here, which is going to be very important for this whole thing, these are positive. In this section, down is the positive direction, right? That's how we're setting things up. Right? Just by convention, that's how they set it up. So we just choose in 3.7, we're thinking of downward direction to be the positive direction. So our gravity is going to be a positive number, right? Because it's going to act downward, which is the positive direction. What else do I need you to know? Preliminary 5. This one relates to springs. It's called Hooke's law.
Well,
You saw this in Calc 2, I think. What does Hooke's law say? F equals minus kx. And again, it's minus. We're using the negative here because down is positive. Right. So basically, if a spring is hanging, which is in our system is going to be hanging, gravity's pulling it down. The spring constant is going to be the force by Newton's third law. The spring is going to want to push back against gravity, and so it's going to push in the positive direction, which is it's going to push in the up direction, which is our negative. So that's why it's negative here. F is called the force that stretches the spring a distance x beyond its natural length. It doesn't really have to be stretches or compresses. So this is the distance, x is the distance stretched or compressed. Beyond its natural length. This constant K is called our spring constant. Right? It's sort of a constant that describes how much force the spring is going to push back with. Now, if at any given time that K is too small to fight against the force that's pulling on it, then the spring will just break or deform. Right? So, what else do I want to tell you? Well, they use a different notation here. It's sort of the same, but just to be consistent with the book. Yeah, in calculus, that's how you memorize it. Here they call this the force with the subscript S, that's the spring, and they use L to be the distance. Conceptually, it's the same thing, it's just different notation. I want to keep things consistent with the textbook in case you want to go over and read it. Okay, so here are the preliminaries. No, that's sort of what we need to know for the background to get to the setup. So let's actually do this. Our goal in this section, measure the motion back to preliminary one, we're calling it U with the following setup. So the spring is hanging, this is the spring. Let's say it has length L, right? So this is just the spring. Now we can attach a mass to this thing. That's going to stretch it even further. The distance it's stretched now is, I'm going to call that U. Or, no, our notation is L. So we have So I put a mass at the end of this spring, and it stretches it by an additional distance beyond its natural length by big L. And so the thing is, if the mass stretches it down, and we're saying that, you know, some sort of oscillation starts to happen. So the spring, the mass itself is going to be bouncing up and down by some distance, which that's what we call U. And then this distance is, of course, going to be L plus U. So this is just the mass in equilibrium, but if there's a situation where it's just bouncing up and down like that, that's the distance I want to be able to measure. The distance that the mass is moving. Right? That's the goal. Figure out what function governs how this part is moving here. Okay. So let's start with the setup, and we're going to use our preliminaries. There's a lot of physics in the setup here, but once we get through that, the situation is going to be modeled by a second order differential equation with constant coefficients, it turns out. So we're basically going to derive the formula, and then I'm going to show you how to get the pieces, and then we're going to be doing the problems that I just gave you as a handout. Yay.
Well, I wonder how I don't know how to do this.
Don't know how to do what? Are you kidding? So you know how to do it?
No.
Okay, let's do this. So, phi P3 the forces acting on mass due to gravity are mass free body diagram. It's a free body diagram, right? So you have the mass here, and we're going to examine the forces that are acting on it, right? First, the mass is here. Its own weight is pulling down. That's due to gravity. But then the spring constant, the thing that's attached to the spring here, is pushing back against gravity by Newton's second law. It's going to push back with the force given by Hooke's law, while its weight is the one pulling it down. Right? So if the spring is in equilibrium, what must happen? They must equal each other. Equilibrium. Meaning a state of rest, it's just everything is equal. Then we must have mg equals to minus kl. They must be equal, and that would keep the thing steady, which I want to rewrite as mg plus I have mg minus, the sum of all the forces must equal 0. So it's actually mg minus k equals 0.
No.
Sum of forces. Now, by preliminary 2, we're going to look at the force, which we had this equation. We're going to come back to that later. I think I also numbered that because we're going to use it later. Now let's examine f of t. So try to follow if you can, but you won't need to do the setup every time you're doing one of these problems. We're going to actually, once we get to the final formula, the setup is going to be easy. But it's sort of nice to know where it comes from. P5 gives us that the spring constant this is during So remember, originally we were stretched by L, but ultimately in our system, if this thing is bouncing up and down, the distance beyond the natural length is L plus U. So Hooke's law gives us this, and so this is force system. Another force. So essentially what I'm doing, I'm trying to find all the forces acting on the system, then I'm going to sort of add them together. And from that we're going to develop a formula. Another force. The so-called damping force. Or resistance force. Right. This is, for example, air resistance.
Or internal resistance.
Air resistance, for example. So there's just going to be some force trying to stop everything from moving, inertia. Okay, so we want to be able to compute this force for simplicity. There are actually many ways you can compute this force, but one of the simplest ways is the following. We assume this force is proportional to the velocity that you're moving. Proportional. It's one of the many ways to describe this force. So you're sort of thinking about it, if you're walking, you don't really feel like you're fighting against air too much, but if you start running, you feel the wind in your face, right? The faster you're moving, the more the air is going to try to stop you. So that's sort of the idea that we're using here, right? The faster something's moving, the more resistance it's going to encounter. And we sort of assume it's proportional, and the constant of proportionality is what we're going to be calling the damping constant, or the damping coefficient. E FD, which I'm calling the damping force, is going to be equal to, and again the negative sign here is because down is our positive direction, gamma times u prime. So this is the velocity of the mass this is the constant of proportionality. Which we call the damping coefficient. We're almost at the end now. Just something to note here. Unless otherwise stated, assume negligible damping. Right. Essentially, if they don't mention there's any resistance, they don't mention any damping is going on, just pretend this guy is zero and move on, right? Just
yeah, if you have a damping force, so how can it be that you're holding, when you start off the problem, you're holding this mass resistance out below equilibrium, and you have to pop up, it's going to pop down even lower, you beyond the original equilibrium down? What?
yeah.
See, but if you have this damping force, which always going to slow it down. So how can it go even beyond what you're starting with?
No, because like if you stretch it, right, the spring is going to bounce it back up. Then it's because it's going at a faster velocity, it's going to come down quicker. It's going to be traveling down a larger distance, so it might go back. But eventually, if it's going up, down, it'll eventually settle, right? Sort of to describe how quickly this is happening, we can use the damping coefficient. If the larger this guy is, the quicker it will start to settle. But yeah, it will eventually go like this, and then that's the idea. Anything else? Okay, so this part really applies to 3.8, but I'm just going to mention it here and mention that we consider it zero. We may also have an external force. Right? Something that's not naturally occurring, that for some reason we have that in our experiment, but some external force is what we call we're going to call it F of t. It's the force being applied at per unit time. In this section, we assume F of t equals 0. And you pretty much always assume that unless they specifically tell you, okay, this is an external force, right? Very usually in most finals, this is the case we're dealing with. The case where it's not 0 is really 3.8, which is the non-homogeneous case, but we know how to deal with non-homogeneous things now, so it shouldn't be a big deal when we get to it. And I don't plan on testing you on that in the next test. Maybe I'll put it as a bonus problem, but it won't be in the actual test.
That means he's gonna put it as a bonus.
I see Vincent trying to apply my advice of paying attention. That's good.
Yes, it's like maybe, and that means yes, it's gonna happen.
Okay, maybe means yes, really?
I can't see anything. Thank you.
It's kind of like maybe we're gonna have a test on in the middle of the semester. Yes, we're gonna have a test in the middle of the semester, right?
No, that's not what we do.
Are you kidding me?
Okay. Are we done with the setup now? Are those all the forces? Yes. Finally. Okay. So the force of gravity, the force that the spring is acting, there's a damping force of your surrounding environment trying to stop all the motion, and then there might be this external force. That's all the forces that we will consider in this setup, and now F of t is the sum of all the forces again. And this is the force acting on the spring, right? Now we know that F of t is mass times acceleration. And if I add up all the forces that I described previously, we will have this times gravity, spring constant, the damping force, and this F of t force, or the external force at any given time. And so this here is mg. This guy we have, it's minus kl. This guy we had was minus gamma times u prime. This guy, he'll have to be given, we need more information to figure out what he is. And what is this one?
0.
This is 0 by equation, what equation was that?
2.
2. Sorry.
Sounds right.
The FS was, I used the wrong one. It's that one. Now I expand this mg minus kl minus ku plus minus gamma u prime plus f of t. This one, 0 by equation 2. This means we end up with m double prime plus gamma u prime plus k times u equals f of t. It's a phrase that you might hear, so I'm just going to mention it from the equilibrium position. All right, so our origin is defined as the equilibrium position, the position we'd be in if we just left the system at rest. Okay. But basically, our spring mass system is defined by this guy, and notice that all these guys, m, gamma, and k, they're all constants, right? It's a second order differential equation, linear differential equation with constant coefficients. Now there are some things that you might lose track of since I was deriving this stuff, so I'm going to just tell you the things that you want to keep in mind. First one. Weight equals mass times gravity. So in this equation here, whenever you see m, it's this, weight over gravity. Right? Okay. The second thing I want you to remember is K equals W over L. So this is length stretched beyond the natural length and stretched beyond natural. And they'll usually tell you what this is. We're going to be reading the questions and seeing this. Another thing to mention, students often forget it. Weight is a force. People often confuse it with mass, but it's not. And here, usually measured in pounds. Right? So if they are telling you something in pounds, you can sort of think of it as weight usually, especially if they're talking about the mass. The moment this pounds, they're telling you what's the weight of the mass, right? Gamma is equal to resistance force divided by velocity. And we'll see how to apply that in our problems as well. Another thing to keep in mind is units. Consistent. In particular, they should match up with your G. So G is equal to 32 feet per second squared. Make sure all lengths are in feet. Be in feet, for example. If you're using the 9.8 meters per 9.81 meters per second squared, then you have to make sure all your lengths are in meters. So, yeah. So that's basically the setup. So basically, this guy describes the motion of the mass at the end of a spring mechanical system. One that's hanging vertically in the So that's going to always be the equation. They're not going to tell you the equation. You just have to know that that's the equation. Okay. Let's actually see the kind of problems that you're expected to solve. We're going to start with the first one that I gave you on the handout.
What handout?
Pay attention.
Okay.
So we're looking at spring 2011. And we'll be looking at 8A. So it's a part of another question, so you weren't actually asked to solve your differential equation, but I'm going to want to solve it as well. We'll do that just for fun.
Just for fun.
We will solve it, though we weren't asked. All right, so on this final, they just asked you to set it up. They didn't ask you to solve it because there was a part B, but I'm going to ask you to solve it, so we're going to solve it. Well, like I always say, pay attention, read the problem, only do what you're required to do, and don't do anything more. You don't want to waste any time. Okay. So let's read through this. A 2-pound weight stretches a spring 6 inches to a position y equals 0. So they're using y instead of u, it doesn't matter. Set up an initial value problem, the differential equation with the initial conditions for the position y of t if the spring is stretched down another 6 inches and then released. So, what are we going to need for this setup? Remember, we're going to use mu double prime plus gamma u. Well, we're using y in this case. Doesn't matter. And y prime plus ky equals 0. No external force was mentioned, so we assume it's negligible. And we want y of 0 to be initial position. So that's the initial conditions they're talking about. And y prime of 0 to be initial velocity. Okay. So what do we need to find here? Well, we're going to need to find the m, the gamma, the k. So let's start with the m. How do we get to the m? Yeah? Right, we have mass is equal to weight divided by gravity. Our weight here is 2 pounds, a 2-pound weight. So we're going to take 2 pounds, we're going to divide it by gravity. I'm going to decide to use the 32 feet per second, which means I'm thinking of all my lengths in terms of meters. So my m here is 1 over 16.
In terms of feet.
In terms of feet. Agree?
Or 16th, what is the unit?
What is the gamma? Okay. Did they mention a resistance force? Assume it's negligible, right? That's one of the notes I said. So they never mention, oh, there's resistance. You know, so we assume it's negligible. It's not going to factor into our calculations, right? So resistance not mentioned. That's why we assume that resistance not mentioned, meaning they don't think it's important. So we won't think it's important either. Then we're going to use to find the k. Now the k is what? The weight over the distance stretched, right? So the weight was 2 pounds, and what is the distance?
Half.
Half a foot, right? So they said 6 inches, but because I'm using gravity to be 32 feet, I need to make sure all my units are in feet. So this is 1/2 foot. I have to use the foot, right? That's equal to 6 inches. So this means k equals 4. Yeah. Mhm.
So for the weight, shouldn't we get it in Newton? The weight?
No, we're going to think of this in foot pounds or something.
As mass, like we don't need to times it by g.
No, we divided by 2.
We divided by g.
Yeah.
We're finding the mass, not the weight. We know the weight. Weight is equal to mass times gravity, so the mass equals weight
I
over
was
gravity.
talking about the last one actually.
Yeah.
For 2, we don't need to do 2 times 9.8 or 32.
No, what?
No, this is the k is the spring constant. It doesn't really care about gravity. It's the force that the spring has to push back against whatever is stretching. So in that case, k is equal to 4. Therefore, what do we have? 1 over 16 y double prime plus 4y equals 0. With, what's the initial position here? It's 0, right? Because they told us that, right? The initial position is 0. Wait, did they say that? No, it's been stretched down another 6 inches, so we're not actually starting at 0. What's the initial position? A half, right? Remember, we have to think in feet.
Oh, yeah, right.
And it's positive because it's going down. What's our initial velocity? That turns out to be 0. Again, it was released. Right? This means we didn't apply a velocity, we just let it go and let it do its own thing. Right? So that's actually the setup. For this final, that's all you had to do, but we're actually going to go further and actually solve it, just for fun. So how do we solve this?
16 1 over 16 after plus 4.
Okay. What does that give us?
Times 16.
Huh? multiply by 16, 4 times 16 is 64. So this means our r squared is minus 64. What does that mean for r? R is plus or minus 8i. Right? It's a complex number, it turns out. So that tells us what our solution should look like. Yes, cosine and sine, which actually makes sense to us, right? It's an oscillating thing. So bouncing up and down by cosine and sine. So again, here's one of the ways that, you know, we're complex numbers, they're not real. Well, it shows up in a real life situation, right? Okay, so we have a very normal situation happening here, and complex numbers pop up. It actually tells us that our y should look like c1 cosine 8t plus c2 sine 8t. And for us, this makes sense. It's going to be oscillating, right? So now we need to, since we're given initial conditions, we're going to want to find the c1 and c2. How do we do that? First, we're going to find the derivative, so we can plug these guys in. So this is going to be minus 8c1 sine 8t plus 8c2 cosine 8t. And we know that y of 0 is equal to a half. That means a half is equal to, you plug in zeros for t, you just end up with c1, right? Because sine of 0 is 0. So that's our c1. And if y prime of 0 is 0, that means I plug in 0 here. And so I just get 8c2. So I get c1 is a half, and I get c2 is 0. This means the position of the spring will be given by 1/2 cosine 8t. Question, is that realistic?
No.
No, because what does that mean?
It means that it will go on
It will
forever.
vibrate forever and never stop, right? Not realistic. Why?
Conservation. Well,
Because we
thermodynamics.
sort of,
Real life this happens.
well, not why that. I mean, why was that mistake made? Well, it's because we assumed negligible resistance. There will be resistance, right? So that could only hold up as an approximation for a very short time, because it will not be the case that this thing is just going to vibrate forever, right? We get a more realistic expectation when we actually we include resistance in it.
Yeah.
Yeah, so that was that. Wasn't so bad, right? Was it?
Well, 207 and 208 made it look bad.
I mean, once you get the setup, it's not that hard. You won't need to derive it. Yes, I wrote here for fall 2011, it was pretty much the same as spring 2011. They just changed the mass, so I'm not going to do that. Let's jump to spring 2006. Try that one. This is a good one. So we are doing problem 12. A mass width, and they told us the m. M is 2. Is connected to a spring with spring constant k equals 4. So they're just giving us everything. The damping is such that when the mass is traveling at a velocity of 1 foot per second, the resistance is 4 pounds of force. So now we're told about damping. So we're going to have to figure that out. Suppose the mass starts at its equilibrium position with a downward velocity of 3 feet per second. Answer the following questions. Find the general equation for the motion for the system. And after 1 second, you held your hand 2 feet below where the weight starting position. Would the weight eventually hit your hand? That's a question. How far will this thing go after 1 second? So again, we're going to use n u double prime plus gamma u prime plus k u equals 0 because they did not mention an external force. M was 2. They gave that to us. That's great. K is 4. Again, that was given. That was very nice. Now they're describing resistance. When the mass is traveling at a velocity of 1 feet per
4
second, the
volts.
resistance is 4. So gamma, remember gamma is resistance force over velocity, right? So this is just 4 over 1. So our gamma here is 4. This gives us that our m is 2, u double prime, gamma is 4, u prime, and k is also 4. What is our initial condition? U of 0 and u prime of 0. So it says, suppose the mass starts at its equilibrium position. What position is that? 0. With a downward velocity of 3.
Right.
Just 3, right? Down is the positive direction. So I know a lot of you are tempted to put the negative here. Do not. Down is the positive direction for our set.
Okay.
So, yeah, and now we just need to solve that because we have to answer these questions. Find the general equation of motion for the system. How do we get to it?
Find the y verse and then take the root.
So where do we start?
Yeah, 2R.
2r squared plus 4r plus 4 equals 0. You can divide by 2. How do we solve that? It's not factorable, so quadratic formula, which is
Minus 2. That's 1 squared plus 4. Minus 4.
e squared
4ac.
minus 4
AC.
times a times c. So this is 8 all over
2.
2a, right? So this is minus 2 plus or minus 4 minus 8 would be minus 4. Take the radical of 4, you get 2 I all over 2. So this is given by minus 1 plus or minus I, which means what is the thing that describes our system? This gives us that u is equal to
C1 e to the negative t cosine t plus c to the negative t.
Now that's more realistic, right? As time goes on, your exponential is going to make this thing small, right? It's going towards 0 as time goes on. Far more realistic here. Now we need to find, we are given initial conditions, so we're going to need to find that C1 and C2. How do we do it? Find the derivative. We're going to need the product rule, so we're going to have minus C1e to the minus t cosine t, minus C1e to the minus t sine t, minus C2e to the minus t sine t, plus C2e to the minus t cosine t. So we know that u of 0 equals 0, which is, I plug in 0 here, I would just end up with C1. So I know C1 is 0. I also know that u prime of 0 is equal to, now I know C1 is 0, so I can ignore all the parts with C1, and I'll just end up with, this is also 0 because of the sign, so I just basically end up with C2. So this is 3 equals C2. This means u is equal to C1 is 0, C2 is 3, e to the minus t sine t. This was the answer to part 1. If you held your hand 2 feet below where it started, will it hit your hand after 1 second? Right? Notice because of the e to the minus t, your oscillation is actually exponentially decreasing, meaning it starts here. As time goes on, it's getting smaller. Right? Basically, we want to say, okay, if after 1 second, will this thing ever dip down by more than 2? Will it actually hit your hand? That's what we want to do. Right? But notice that it's getting smaller. It actually makes our problem easier. If I look at u of 1, after 1 second, what's that going to be? It's 3.
3 e to the power of 1.
Sine 1. And that is definitely less than 2. And it's only getting smaller, right? So at 1, it will be this distance, but it will only get smaller than that, right? So it will never reach 2 after 1 second. It will not. Remember, e is 2.7 into there. So 3 times this is slightly bigger than 1, but sine of 1 is less than 1. That's maybe 0.8 or something. Right there. That was one of the more difficult questions that you'll see. Let's look at another situation. Fall 2006. Problem 9. Okay, a 4-pound weight in its equilibrium position stretches the spring from which it is suspended by a half a foot. Beginning in its equilibrium position, the weight is given an initial velocity of 4 feet per second downwards. Air resistance, which is proportional to velocity, is 8 pounds when the weight has a velocity of 8 feet per second. Find the function u of t which describes the displacement in feet of the weight t seconds after its release. Assume gravity is 32 feet per second squared. So, again, when we double prime, that's down in prime, that's ku. They did not mention an external force. Let's go through, find these. What is M? It says it's a 4-pound weight, and so it's 4 over 32, which is 1 over 8. And what else do we need? Gamma? How's gamma 0? It's resistance force over velocity. It says air resistance proportional to velocity is 8 pounds when the velocity is 8 feet per second. It's actually 8 over 8, which is 1. Let's look at K. K would be the force, which is the weight, divided by the length it's stretched. 1/2. So here K is 8. So now we just plug these in. So we have here 1/8 u double prime plus u prime plus 8u equals 0. Our initial position is 0. Because it says it beginning at its equilibrium position. It's given an initial velocity of 4 feet per second downwards. Now we solve this. How do we solve that? And multiply by 8 if I want. Does that factor?
No.
No. And it, by the way, that's normal. It usually won't, right? Because you need the sine and cosine. Otherwise, it won't be realistic at all.
What's 4 times 16?
So R would be minus B plus or minus the square root of B squared minus 4 times A times C all over 2A. So this is minus 8 plus or minus, I can factor out a 64.
Is it minus 8 or minus 4? Because you.
Come again?
Oh, I mean, couldn't you divide the 8 into 2?
Yeah, but I'm working on the top first.
Oh,
I'm going
okay.
to do that later. I can factor out a 64. This would just leave me with minus 3 under here. So that would give me minus 4 plus or minus 4 radical 3 up. Which means my u is given by c1 e to the minus 4t cosine 4 radical 3t plus c2 e to the minus 4t sine of 4 radical 3t. Gonna have to find the derivative to plug in the initial conditions. Minus 4c1 e to the minus 4t cosine 4 radical 3t minus 4 radical 3 e to the minus 4t sine 4 radical 3t minus 4c2 e to the minus 4t sine 4 radical 3t plus 4 radical 3c2 e to the minus 4t cosine 4 radical 3t. So u of 0 equals, if I plug in 0 here, the 0 will kill the sine. Cosine will be 1, so that's the c1. So c1 is 0. U prime of 0 is equal to 4. So c1 I know is 0. There should be a c1. 4 radical 3 c1. c1 I know is 0, so I ignore this term. I ignore this term. This term has a sign in it, so I can ignore that term because sine of 0 is 0. I will ignore this. So I just get 4 radical 3 c2, which means that c2 is equal to 1 over radical 3. This means my u is equal to 1 over radical 3 e to the minus 14. So, 4 radical 3t. And I didn't mention this last time, but you can check that your solution actually makes sense, because if you plug in t equals 0, you actually start from 0, which is what they said. You start from the initial position, and then it gets smaller as time goes on. There are 2 more problems, but I leave those to you. This will be a part of your review anyway, the final questions from the final. So try those on your own, and on Monday I'll take questions. The review problems should be up to date, and
Good luck.
good luck.